Hi. Before starting, I wanted to bring up this disclaimer that this is not financial advice. I am not professionally trained nor legally trained in the fields of finance, and the motivation for this video is purely educational. So with that, I also wanted to bring up that I'm not endorsing any strategy explained in this video or beyond in the material of this video, tied to this video. And so with all that, I would just like to, I think it would be prudent to take all the content here with a grain of salt. Now, besides that, I just wanted to give some credit with credit is due. Eve's Hillpish's books were significantly helpful on understanding on how to look at financial data, the plotting, and some of the material from his book helped significantly in building up the plots. Even the analysis itself also was quite helpful. And so I wanted to give credit also to the analysis that he showed on support vector machines in his 2018 book. I also wanted to give credit to this third source, which helped understand how cumulative, like total rate of return, translate to cumulative logarithmic rates of return from its components. And source number 4, it's basically the title, how to download cryptocurrency data using Binance API. Number 5 is an article by Lei Jiang and Junmin Zhao from 2016, and it was quite helpful in really understanding support vector machines and how C-support vector classification works. Without further ado, we'll start going over the bulk of this video. This section was explained more fully in another video of mine, so I will be providing the link below video description for that one. I will not be going so much into this material. I just need to rerun this cell to get process some of the data below. Now, the bulk of this video will be dealing with analysis, not analysis, but looking really at support vector machines and the algorithm, how it can be used to look at close price differences or forecasts even, and not so much we'll be going over real-time forecasting, but just looking at how it can perform from previous historical data. And of course, that was a concept shown in Heath Hillpish's 2018 book. Now, for now, the only thing you need to understand about support vector machines is that they just work as a classification algorithm. It's basically getting a bunch of data and boxing them into two different classes. I'll be explaining the method more fully below. Computing returns, this is something that I've explained on a previous video of mine as well with the layman terms, so as much layman as it can go. It's basically this rate of return. It's just the rate of change between initial price and final price at a specific time t. You can rearrange that equation, and we end up with, take the logarithms of that rearrangement, and we end up with equation number 2 here. And then, of course, we can rationalize that this logarithmic rate of return over a specific time can be equated to the sum of its logarithmic components of component rate of returns. Right. So if we, for instance, wanted to look at rate of return from a candle at 1 hour from candle at 1 hour to candle at the beginning, or candle at hour number 2 from candle number 1. This is basically how they compound, and then we can obtain the total rate of return from that. And that is something that is already being, that will be computed in this using this function here. So you can even start seeing some of those computations going on in the first 3 lines of code here. Line number 1 is just basically taking all the closed data and equating it to the data variable. We can make up a new column or data frame variable called market, and that would actually be all the rates, all the logarithmic rates of returns in the data frame. So this is how it's done. By shifting, we just basically are dividing over the past data point to the current one. And of course, we're just dropping 1, which would be the beginning point, data point, which is empty because there is no shift. Because the shift would end up giving an empty space at the beginning. And this is actually the lag cross price differences are the data which needs to be made to do the vector classification. Now, this will require understanding of both vector classification with SVM, as well as really what lag close price differences are. So let me think about how I would explain this in the simplest way. I guess we'll look at the data which we're generating for the classification first. These are what are lag close price differences, right? So this section deals more with the data generation. Now this is the schematic which I've thrown, and of course it's just made up prices just to show the concept. And it's really very simple. So each of these, if we look at the data, every data frame from, let's say, any market whatsoever, you could imagine at time equals 0, we get 100, then maybe the crypto increases in price and it goes to 150 and so on and so forth. Each of these from the second value, because of course these are all logarithmic rates of returns which take the fraction of the current one over the past one and then take the logarithm of that, then we can obtain that market column we generated in line 2 of this function. And so all of these are just rates of return, logarithmic rates of returns. In order to make that or this lag data, it's really just taking the sign of that logarithmic rate of return. So for these cases, these two first rows were positive, so they get a value of +1. This one was negative, so now -1. And what we basically do is we just copy paste this column 5 times, so we end up with 6 columns. And that's what the lag is actually shown here in this larger table. So a lag, what it does is it shifts, and of course all of those columns above, because they're copies, they have the same values. We just shift them 1 value ahead and each of the columns consecutively 1 value ahead from the previous one. So you can see that then we end up with here on the first lagged column, it's actually looking at the sign, not from the current one, but from the past, from a previous logarithmic rate of return for 43, because it's shifted. And so this one is also from -78, negative, 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 positive, positive, and so on and so forth. So this also implies a reduction in the number of rows. So in the end, for 6 shifts, we just, and this, the row size, the size of the row size, right, of the table, we end up with just being able to use 2 rows because it's shifted 6. And so for this case, what we do is really we can also, I mean, besides these shifts, right, we can also take the original unshifted column, and what the support vector machines does is it tries to correlate all of these lagged data to the actual sign, and in doing so then it can come up with a prediction. So that's the last column In this case, for instance, it tried to correlate as best it could with all this data, or really the few points thereof. Correlation wasn't not great, so it could not predict the second sign accurately, or the last sign accurately, so it got -1. And so that's basically the data generation. It takes all of these lagged rates of return signs to predict the actual sign. And in doing so, it can try to predict future data. Now, how do support vector machines really work? Are they actually, a linear combination of coefficients? Well, I don't think so. They may be something a little bit more complicated, which I will show here. This is a drawing I made, which I think explains the concept quite nicely. Imagine you are dealing with a two-dimensional plane, and this is just 2D, or just actually imagine that it's 2D. In a two-dimensional plane, every point can be actually seen as a vector. Actually, in any hyperdimensional plane, any point can be seen as a vector. That vector should be a linear combination of the position or direction and the magnitude of the point on that space. So let's say we're looking at point 1. Point 1 would then be a linear combination of the unit vector, which is called unit vector 1, times the magnitude x1, plus unit vector 2 times, let's just say x and y, right? So x and y, let's say it's at a value of 4 on the y-axis and value of 1 on the x-axis, then here x equals 1, y equals 4. And so that's how it can be expressed. So in theory, all of these points are actually vectors or arrows in the 2D space. Now, in 2D space, you can classify a series of datum by just dividing them with a line or a barrier. And that's actually what the support vector machine vector classification is doing in the most basic sense. It is just trying to come up with the most optimal barrier to divide data points into two classes. And it's not really doing it in 2 dimensions. It is doing it in several, it can be done in several dimensions, which span beyond the 3rd dimension even. So let's say for our case, we are dealing with 6 lags of time. It's doing that 6-dimensional, it's looking at 6-dimensional space. And this is why this line is really a plane at that level, and why this whole thing, line, with a specific also constraint or specific, what do you call it, a deviation, is known as a hyperplane. And so in a similar way, if it's 6-dimensional space, we are actually looking at linear combination now of unit vectors, which span all the way, actually in this case would be u6, but let's just go to the general sense, un times xn, and then we can just convert these to x2 and x1. So every point, no matter what its dimension, can be represented as a vector, mathematically at least. And the hyperplane, we can do that in a very similar way. A calculation of the optimal hyperplane is done in support vector machines, and that is what is doing the classification. And so what we have here, and what we were looking at before, was it events? Yeah. And what we were looking at before is really these signs. They could be either +1 or -1. So we could imagine that +1 is in this part of the hyperspace, and on the right side of this hyperspace, and then -1 could be maybe on the left side of the hyperspace divided by the hyperplane. Right? And where are the other dimensions, right? Well, the lags. I think that's good enough for an explanation. And so what we're doing here is calculating all of these to really fit the data so we can obtain a good classification. Now the last of the remaining points are just quite self-explanatory. Actual sign, right, is basically taking the logarithmic, what I explained before, taking the logarithmic rates of returns and just calculating the sign. This actually NP sign is the same thing, right? This is how you're you're actually running the machine learning here to fit the actual signs, data columns. Sorry, not the data, not the actual sign. The actual signs here to the lags, close price differences, close price. Actually, this should be lagged signs, right? Okay, to the lagged signs, which are all these columns. That's how it's doing the fitting. Prediction. This is just to create a column that will give you the predicted sign. And in doing so, of course, then we can compute the actual market with the data prediction. And then from that, we can obtain, by taking the cumulative sum of those, which is basically what's going on at each of these points, right? We're taking this one, and then we're looking at the point, and we're taking this one plus this one, and so on and so forth. And then we're taking the exponent because we don't want them in logarithmic form. We want to express the total rate of return in natural form. So that's what's going on there. Strategy again, it's just find a theoretical ROI, quote unquote, times 100 because I'm just putting it in percentage. And that's basically it. That's the bulk of this algorithm. So we run it. And now we're looking here at this section function. This is the utility helper function to plot all the data using the MPL finance module. So for this, you can see that I've used this is why I made some extra data frame columns above just to plot them nicely in the plot, which you will see below, the actual sign, the prediction, all these the different cumulative rate of returns as well. They're being plotted along with the the cryptocurrency data as well, which is here. So that's basically that function which makes it. Now candles, coin, market, just basically which candle time frame we want to look at. I'm just gonna do 1 minute candles. Coin, from the title of the video, just Bitcoin on the USDT market. And this coin pair, of course, is that function. Actually, no, coin pair is the function which downloads the cryptocurrency price data. In this case, Bitcoin USDT, and then backtest is just, of course, this helper function which does everything. And the helper function calls into the strategy compute to get all the data, of course. So we run it, and we'll see what we get. Okay. So we get just a couple of things I've really written here. As I mentioned, the quote-unquote theoretical real ROI seems to be 11.31%. And that would be the final, so it would be the ROI here, the last data point, the last part, at the end, sorry, of the whole chart. What other thing does this show? Yeah, so this prediction plot in the chart, the orange one is actually the predicted sign, the predicted signs on the logarithmic rates of returns for the specific candles, right? And the blue is the actual sign. So if you see more orange, or you see full orange, that means that you have a very good prediction. It means that it's predicting a lot of points, because it's the overlap is so large that it completely obscures the blue. However, we can still see some of the blue here. So there may be a better quantitative way to do it, to maybe show how many did we really get right. And so that's what I will be doing above. So maybe I should do that above. How do we get all of these? I'll just create a new column called accurate. And accurate will be a column which will just be a boolean, pop out or output booleans, where basically want the actual sign be equal to the predicted sign. Right, so if that's the case, then we get let's get a 1. And if we don't, we get a 0. Okay, so that's accuracy. So true, false. Now maybe helpful if we go a little bit beyond that and we look at really how many we got right. So we can just call that number accurate. Number accurate would be equal to data accurate and basically where data accurate is greater than 0 or equal to 1, and then the sum of that. So that would be a number accurate. Okay. And now we will just print, we can then see percent accurate. We'll just call accuracy. Would be equal to the number accurate over data accurate. So the shape, the first index of the shape, which would be the number of rows. That should be good. Okay. So now we can just set up also a printing statement. Print accuracy. Sure. We can call it AI accuracy even. Accuracy times 100. And let's just like round it, not round it, but take floor division or floor rounding with integer. That should be good enough. Okay, so that will give us a percentage sort. Run it again. We'll run it again, and now we should get AI accuracy now. So 64%. So that means that 64 out of 100, right? Did it get it right? Did it get the prediction? Was the prediction accurate, or was the prediction? Yeah, was the prediction accurate for that data point in terms of like the sign of the rate of return? And now we're getting 14%. The reason why we're getting more now, it's because we're looking at 1 minute candles, right? And 1 minute changes every minute. You see, 13.73, 739. But the AI accuracy is consistent nonetheless. So that's good. So of course, when you're looking at 1 minute or very fast, I don't know what they're called really, instant Instant trading? I wouldn't even go that far, right? What do they call it? Short trading? I don't know. Anyways, I digress. So we could go to a longer time frame or longer candle. 1 minute, maybe we can go to 10 minutes. Can we? API Binance? We cannot. 30 minutes. You can go to 30 minutes and you can see the theoretical final return of investment, 54%. That's much greater, but accuracy is still 64%. That may be because there are more data points perhaps here. And so more data points implies more trading regimes. As you can see, there's like way more here. And so there's more chances of taking into advantage specific spikes and whatnot. And we can go to even like larger, 1 hour. Let's see, 1 hour candles are popular, I think. 1 hour, 88% accuracy, not 88% ROI, final ROI. Still 64% accuracy. Let's go to 1 day. See, it dropped. AI accuracy dropped to 62, from 64 to 62%. But final theoretical ROI, 943%. Significant increase from the previous one, which was 82. Like 1 order of magnitude increase in percentage, which is huge. At the expense of AI accuracy of 62%, you will think, why? Our accuracy dropped. More data points. More stuff to, quote unquote, I think, more stuff to trade. Don't quote me on that, of course, it's as I mentioned, not financial advice. We can go to 1 week. You can see accuracy actually increased. And so did return on investment by 1 order of magnitude again from the previous one. Huge. Let's go to 1 month. ROI decreased. Theoretical ROI. Accuracy increased, however. That's maybe because now we are dealing with less data points. And you can see how that changed, right? Again, 1 month period time frames. And so that may be a good explanation perhaps for it. And so with that, there's of course, wanted to bring up once again this chart. Which chart? Events. And the chart, just wanted to bring this up because we are not looking at the future per se. The last data point here, it's predicted, but for that sign that already happened. It is not looking for the next which has not happened yet. That of course can be done easily. You just need to understand the shifting, right? And get like basically the price for the current one, and then do the shifting yourself. And so you can, in principle, you could just build it. And I'm not going to build it here because it's not the intention, as I mentioned. I just wanted to really show this as an educational thing. And yes, so that's why I wanted to bring it up, that all of this is actually fitting. And even the last point here is not looking at the predicted sign for the next one. It's looking at just what was predicted for that specific sign which already happened. All right. And I think that would be it. I wanted to stress that disclaimer again, that this is not financial advice. And references, which I believe I talked about in the beginning of the video, already talked about it, so I will not mention it again. But however, just wanted to really give credit to that. So I think they're really good resources, or they were at least for me. Of course, if you wanted to compile it as a PDF, just like uncomment this, run it. If you would change the name of your notebook, you may need to change it here to get a document. And your document, after you compile it, should come up here on this section. Just gonna what happened? I'm just gonna uncomment it and gonna save. Maybe not. All right. So I would say that this is the end of the video. Of course, if you really liked it, just there is a like button somewhere there below the video description, under the video description. And so consider giving it a like if you'd like. And also, of course, if you really like all the material you're seeing, there may be some potential cool material later on that I show. So be sure to subscribe also to my channel if that's the case. All right, so that would be it. Thank you.